So let me start by thanking the organizers for giving me the opportunity to present our work. And this is actually the first time I'm attending this series of meetings, and it's been great. So I'll be talking about some of the recent developments in the series of work that we have been doing for a while. So the collaborators are In-Shen He, who has been doing most of the work. He's a postdoc at Max Planck Dresden. Gyohei Fuji, who is also a postdoc in Dresden, and Frank Pohlmann and Roderick Mosner, also in Dresden. And these are the references. And I'll talk about mostly about the latest installment of our work. Okay. So one slide for the definitions. So I had the two words quantum spin liquids and deconfined criticality in the title. So let me give a very brief introduction to what these two things are. So as Kedar gave introduction to what can happen in frustrated magnetic systems. So that the magnetic order is suppressed due to competing interactions. So what can happen in, I'll be talking about systems in d greater than 1. And what can happen in such systems is that in these magnetic insulators, the magnetic order is completely suppressed even at t equal to 0, and we end up with ground states which do not show any long-range magnetic order, or what is more defining is that there are very exotic excitations which have fractionalized quantum numbers. For example, we can have quasi-particle excitations which carry spin half. Remember, we are working with magnetic insulators, and so we are well below the single particle charge gap, and so these are not electrons. So that will suffice for the rest of the talk, the definition. So moving on to what deconfined criticality is. There are a class of continuous quantum phase transitions that we encounter. These are zero temperature phase transitions, as Raja was talking about, that are not captured by this Landau's order parameter based critical theories. So here are various examples where which can where you cannot construct Landau's order parameter based critical theory to describe these general continuous transitions. And so these class of transitions have been dubbed as Landau forbidden transitions, and the class of such transitions the critical theory is actually written in terms of fractionalized fields which appear only at the critical point, but are generally not present in the phases. So these type of phase transitions have been studied for a while now, and they're called deconfined criticality. So I'll discuss one type of deconfined quantum phase transition in this talk. So studying this kind of unconventional phases and phase transitions have been one of the central things in quantum condensed matter for a while now. And I'll speak about a particular problem in this talk. So basically, the problem is quite easy to state. So this is a Kagome lattice, two-dimensional lattice of corner-sharing triangles, and I have the spin-half nearest neighbor Heisenberg model on this lattice. And the question is, what is the ground state of this Hamiltonian? And this is not only a theoretically interesting question, but we have concrete material motivation to study this problem. This material, Herbertsmithite, which has been worked on for a while now. The copper carries spin half, and these are these green atoms sitting on this Kagome lattice. Okay, so the theory problem is quite old, and I have actually not even dared to list all the works that has been done, which would take several slides. But the experiments are more recent. So what we know about this problem is that the ground state most likely is not magnetically ordered, which is consistent with this material. The experiments on this material show that there is no signature of magnetic ordering down to very low temperatures. And presently, the most viable solution for the ground state of this model seems to be what is a quantum spin liquid state. But the open question is that what is the nature of this quantum spin liquid? So, so this problem is pretty hard to make analytical progress, because since there is no perturbing parameter in this Hamiltonian, which can give good access to this quantum spin liquid, whatever perturbing parameter people worked on gave rise to magnetic orders for a while, and there was a feeling that was being gradually developed that this this model is sitting very close to a critical point, and whatever perturbations one may add to this model would move it into a different phase altogether. But recently what has been found is that there is a class of perturbations, the so-called XXZ model. So you add, you make the Ising couplings, the ZZ couplings different from the XY couplings. This is the nearest neighbor part, and you also add the second nearest and the third nearest XY couplings to this model. And the good thing about these perturbations, yeah, SU2 invariant perturbations. So there were also Dilushensky-Moria couplings added. Okay, so this shows that so recent DMRG and ED results show that the spin liquid. So here is the Heisenberg point, and the spin liquid. This is the second and third neighbor couplings. The spin liquid is actually stable to these anisotropic perturbations, and in addition, for large values of this, the third neighbor and second neighbor couplings, you get another spin liquid, the so-called chiral spin liquid, which spontaneously breaks time reversal symmetry, and this thing has been also around. Such concepts have been around for a while now. So the question is that whether one can use this extra energy scales to get a insight to this Kagome problem. Okay, so particularly one interesting limit is this easy access limit, where the Ising perturbations are bigger than the XY perturbations. Okay. So in this limit, suppose I think about the Ising model, in every triangle I have this up, down states, or 6 states per triangle, where if you sum over the spins on each triangle, it's plus minus half. And unlike what Kedar pointed out, the spin correlations of this Ising model are exponentially decaying, unlike the triangular lattice model. So working out in the limit where the Ising exchange is bigger than the XY exchange, one can work out of this classical manifold, introducing the medial lattice, where you introduce spin half variables, these taus, on the center of the triangles, which form the honeycomb lattice. And one can cast this problem into the problem of a Yuan lattice gauge theory coupled to matter fields at a finite coupling for the gauge field. So I'll, for want of time, I'll not go into this, but I'll basically outline the solution that we have for this model, and I'll be happy to discuss this outside the talk. So we take this easy access limit and focus on this limit. So I've drawn the axis now in the horizontal fashion, and note that I have the Kagome spin liquid below here, and the chiral spin liquid, which is now this, and this is described by a Yuan gauge theory with matter at some coupling. Okay, So what we found is that there is some coupling 1 over E naught for this model, but we can ask the question: what happens if we vary the coupling, keep the coupling in general, and different values of this coupling correspond to different models in this phase diagram. And this is the coupling that I tuned to get a transition from the Kagome spin liquid to the chiral spin liquid, something like the second and the third neighbor XY exchanges. So what we find is that at zero gauge fluctuations, where the gauge fields are sort of frozen because the coupling is very large, I have a phase transition from a chiral spin liquid to a magnetically ordered state, and this phase transition has to be a deconfined phase transition because it's a transition between a quantum ordered state and a symmetry broken state. And once you turn on the gauge fluctuations, the gauge fluctuations actually make this deconfined phase extend into an extended critical phase, which according to this solution is the description of the Kagome spin liquid phase. Okay. So I'll briefly just mention the structure of this deconfined critical theory. So the deconfined critical theory are written in terms of this fractionalized fields, which are these F and G fields, which are Dirac fermions, and there are several symmetries in the model, and these are the transformation properties of these fractionalized fields. And this is a critical theory that one can write down, and this is a coupling of the gauge field. Okay, so the key feature of this phase diagram is this. Sorry, this should be infinity. This line where the gauge fluctuations are frozen, and in the line you can see that I have this Dirac fermions, and there is a mass term, and depending upon the type of mass term that I tune in, I can get the either the magnetically ordered phase or the chiral spin liquid phase, and actually adding to the gauge fluctuations open up a deconfined phase at the critical point. Okay, so once I have the mass term, I can integrate out the fermions, and this is the structure of the Lagrangian. Once I integrate out the mass terms, and basically these AC and AS gauge fields correspond to the various symmetries of the model, and so the point is that this is a structure when I have no gauge fluctuations. On introducing gauge fluctuations, I get rid of this mode and get a chiral spin liquid. These are actually the details of the calculation. On the magnetically ordered side, at 1 over at T square equal to 0, I have two Goldstone modes coming from the gauge fluctuations of this and this field, but on gauging I lose one of the Goldstone modes, and that describes an XY magnetic order. And at the critical point I have a massless theory, which is described by the Dirac fermions, massless Dirac fermions. Okay, so here is a summary. So I've described the U1 quantum spin liquid for a Kagome antiferromagnetic phase. This the quantum spin liquid is actually stabilized by the gauge fluctuations, and this process is generally known in literature as gaging. And this quantum spin liquid is necessarily beyond the mean field slave particle decomposition that's known that has been known for a while, and this actually suggests along with a series of works that we have been doing for a while, that there is a generally deep connection between the different topological phases through this concept of gaging. And these are the few things that needs to be answered about this particular problem, particularly the quantum numbers of these fractionalized fields in this quantum spin liquid, and the correlations, various correlations in the deconfined phase, and particularly there is this open question whether this is actually the ground state for Herbertsmithite. Thank you.
Time for a quick question. Can I think of this in terms of a variational wave function?
So these are actually the dual variables. So I have to construct a wave function in terms of the dual variables. In that sense, yes. Oh, sorry. Wave functions for her. Okay. Right. So partial answer to that question is that this does not belong to the same PSG as the Yuan spin liquids that people have been thinking about. That part we have ruled out for now. So those wave functions do not work, but what exactly the structure of this wave function is, that's a harder question because you cannot, so this is beyond PSG. So that's why it's difficult to construct wave function in the usual way.
Subhro, from this easy axis way of thinking, is there a way of thinking about the spin-ons as well, just like in 1D from this easy axis picture?
Right. So basically, these tau variables are the things, and you write this taus as some a dagger a minus half, and these are basically the spin-ons that you excite. So basically, once you operate the S plus and S minus on these sides, you create spin-ons on these sides of the honeycomb lattice. That's this thing that Nikolic and Stenzel pointed out. So these are bosons.
If you go towards the isotropic limit, then is it okay? Can you say something about the statistics?
Okay, so what I didn't point out is that what I didn't discuss at all is that how do I get these fermions? Okay, so that's an involved story, and so basically what you get is you have this bosons, and then these fermions are basically related to the vortices of these bosons. Because there is a theta term in the field theory, the vortices of the vortices of the bosons turns out to be fermions.
Perhaps we can discuss later.
Yeah.